Have you ever gazed up at the night sky and wondered if there's a single, elegant equation that governs everything in the universe? From the tiniest particles dancing in the quantum realm to the majestic waltz of galaxies across cosmic distances, physicists have long dreamed of a theory of everything. This would be the ultimate unified theory, a single framework that explains all the fundamental forces and particles of nature. For decades, this has been the holy grail of physics, a quest that has captivated some of the greatest minds in history. Now, some scientists believe we might be closer than ever to finding it. The journey towards a unified theory began with a simple observation. The world around us seems incredibly complex, yet it's governed by a surprisingly small set of fundamental rules, or forces. We currently know of 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Gravity is the force that keeps our feet on the ground and planets in orbit around stars. It operates over vast distances and governs the large-scale structure of the universe. Electromagnetism is responsible for light, electricity, and magnetism. It's the force that binds atoms together and powers the technology we use every day. Then we have the 2 nuclear forces, which operate on the minuscule scale of the atomic nucleus. The strong nuclear force is what binds protons and neutrons together, overcoming their natural repulsion. The weak nuclear force is responsible for certain types of radioactive decay, a process that is crucial for how stars, like our sun, generate energy. Throughout the history of physics, there has been a powerful trend of unification. In the 19th century, James Clerk Maxwell showed that electricity and magnetism were not separate forces. He demonstrated they were 2 sides of the same coin, unifying them into a single theory of electromagnetism. This was a monumental achievement. In the 20th century, physicists managed to go a step further. They successfully unified electromagnetism with the weak nuclear force, creating what is known as the electroweak theory. This theory describes how these 2 seemingly different forces behave as a single force at very high energies, like those present in the early universe. This success fueled the ambition to unite the electroweak force with the strong nuclear force, leading to what are called grand unified theories, or GUTs. While we haven't experimentally confirmed a GUT yet many physicists are confident that this unification is possible. But there's one force that has stubbornly resisted all attempts at unification: gravity. The problem lies in our 2 best descriptions of the universe. We have Albert Einstein's theory of general relativity, which is our master theory of gravity. It describes gravity not as a force, but as a curvature of spacetime caused by mass and energy. General relativity works perfectly on large scales, predicting everything from the bending of starlight to the existence of black holes with incredible accuracy. On the other hand, we have the standard model of particle physics. This is our master theory for the quantum world, describing the other 3 forces and all known elementary particles. The standard model is a quantum field theory, and it is arguably the most successful scientific theory ever created. Its predictions have been confirmed by experiments to an astonishing number of decimal places. Here's the fundamental conflict. General relativity is a classical, continuous theory, while the standard model is a quantum, probabilistic theory. When you try to combine them, the mathematics falls apart. For example, if you try to describe gravity in the language of quantum mechanics, the equations spit out infinities, which is a clear sign that something is deeply wrong. This is the central challenge in the quest for a theory of everything. How can we reconcile the smooth, geometric description of spacetime in general relativity with the chaotic, quantized world of particles? This is where a candidate for the theory of everything enters the picture: string theory. String theory proposes a radical and mind-bending idea. It suggests that the fundamental constituents of the universe are not point-like particles, but unimaginably small, one-dimensional, vibrating strings of energy. According to this theory, Every particle we see electrons, quarks, photons is just a different vibration of the same underlying string, much like different notes on a guitar string are just different vibrational patterns. This elegant idea has a profound consequence. One of the vibrational modes of these strings corresponds to a particle with the exact properties of the graviton, the hypothetical quantum particle of gravity. In this way, string theory naturally incorporates gravity into the quantum framework, something no other theory has been able to do. It doesn't just accommodate gravity, it requires it. This is why it has been a leading candidate for a theory of everything for several decades. It provides a mathematically consistent framework where all forces and all matter could, in principle, arise from a single entity, the vibrating string. However, string theory comes with its own set of challenges. For one, the theory requires the existence of extra dimensions of space. We are familiar with three spatial dimensions: length, width, and height, and one dimension of time. String theory, in its most consistent versions, requires a total of 10 or even 11 spacetime dimensions. So, where are these extra dimensions? Proponents of the theory suggest they're curled up, or compactified, to a size so minuscule that we cannot detect them with our current technology. Imagine a garden hose. From a great distance, it looks like a one-dimensional line. But as you get closer, you see it has a second circular dimension. The extra dimensions of string theory could be like that, just on a vastly smaller scale. Another major hurdle is that string theory doesn't just describe one possible universe. It describes a vast landscape of possible universes, perhaps as many as 10, to the power of 500. Each of these universes would have its own set of physical laws and constants. This makes it incredibly difficult to extract specific, testable predictions for our own universe. Finding our universe in this cosmic haystack is a daunting task. This lack of unique, testable predictions has been the biggest criticism leveled against string theory. Science progresses by making predictions that can be tested against experimental evidence. If a theory is so flexible that it can describe almost any outcome, it becomes very difficult to falsify, which is a key component of the scientific method. This has led some physicists to explore other avenues. One of the main alternatives to string theory is called loop quantum gravity. Unlike string theory, loop quantum gravity does not attempt to unify all the forces. Instead, its primary goal is to provide a quantum theory of gravity. It tackles the problem by quantizing spacetime itself. It suggests that spacetime is not a smooth, continuous fabric as Einstein envisioned. Instead, loop quantum gravity pictures spacetime as being made of discrete, indivisible chunks, or loops, like the pixels on a screen. At the smallest possible scale, the Planck scale, spacetime has a granular, atomic structure. This approach resolves the infinities that plague other attempts to quantize gravity. Because space cannot be divided indefinitely, there is a fundamental limit to how small things can get. Loop quantum gravity offers a fascinating picture of reality, suggesting that space and time themselves are emergent properties of a more fundamental quantum network of interactions. It has also made some specific predictions, for example, about what might happen inside a black hole, suggesting that the singularity at the center is replaced by a bounce to a new region of spacetime. However, like string theory, loop quantum gravity also faces significant challenges. It has been very difficult to show how the smooth spacetime of general relativity emerges from this granular quantum foundation. Furthermore, incorporating the particles and forces of the Standard Model into the loop quantum gravity framework has proven to be an extremely difficult problem. So, we have these two major competing frameworks, each with its own strengths and weaknesses. But recently, a third intriguing idea has gained momentum, one that might even bridge the gap between these different approaches. It's based on a principle called the holographic principle. This idea, born from the study of black holes, suggests that the information content of a volume of space can be described by a theory. that lives on the boundary of that region. Think of it like a hologram on a credit card. A two-dimensional surface contains all the information needed to project a three-dimensional image. The holographic principle proposes that our entire three-dimensional universe might be a projection of information stored on a two-dimensional surface at the distant edge of the cosmos. This suggests a deep and unexpected connection between gravity, which exists in the bulk 3D space, and quantum field theory, which would live on the 2D boundary. This concept, known as the AD-CFT correspondence, has become a powerful tool in theoretical physics. It provides a mathematical dictionary to translate problems in gravity into problems in quantum theory, and vice versa. While not a full theory of everything itself, it reveals a profound duality, a hidden connection between the world of gravity and the world of particles. Some physicists believe this duality might be a fundamental clue, a Rosetta Stone for deciphering the ultimate theory. It hints that the distinction we make between gravity and quantum mechanics might be an illusion. Perhaps they are not two separate things to be unified, but rather two different descriptions of the same underlying reality, viewed from different perspectives. So, have scientists found the ultimate unified theory? The answer is a definitive number. We have tantalizing candidates and powerful new ideas, but the final confirmed theory remains elusive. The quest is far from over. We may need a completely new idea, a conceptual revolution as profound as the ones initiated by Einstein or the pioneers of quantum mechanics. Or perhaps the answer lies hidden within string theory, loop quantum gravity, or the holographic principle, waiting for a breakthrough in our mathematical understanding or a crucial piece of experimental evidence. The search continues at the frontiers of science, in the colliders that smash particles at near light speed, and in the telescopes that peer into the deepest reaches of the cosmos. Every new discovery, every piece of data, could be a clue that points us in the right direction. The dream of a single, beautiful equation that explains everything is still very much alive. It's a testament to the human drive to understand our place in the universe, to read the very mind of creation. Thank you for joining us on this cosmic journey. For more explorations into the mysteries of the universe, be sure to subscribe to Space Repo.